what is analytical chem? What analytical techniques can we use? How can we use them to analyze? That's what we're going to come out of today. So essentially, what we do in analytical chem is how do we figure out what the compound we have in the first place? So when you have like a solution, you don't know what it is unless it's labeled. So how do we figure it out? This is what we do. Analytical chem uses fancy instruments to separate, identify, and quantify molecules. In Unit 4, we are only concerned with organic compounds. So just like organic compounds, chemistry has billions or bajillion really important real-world implications. Suppose you're at a crime scene, you find suspicious powder, how do you know if it's dangerous or not? Perhaps you get put over the side of the road, you do a random breath test, how do the cops know you've got ethanol in your system? This is essentially the same thing. These all use analytical techniques. So we separate using chromatography. We've discussed these in year 11 already. You need to sort of refresh yourself on these. There are slides on it. I'm going to skip over the slides on it, but I've left the slides in there on purpose so that all of you who want to go over it can click into the slides, scroll down and find those slides and go through it if you would like. There is identify. There is spectroscopy, which is the main proportion of this topic, and you're going to spend most of the time on that. Then there is quantify, and this is like acid, base, and redox. We've been through these before. We went through these in sort of topic in like Unit 3. Acid, base is sort of like titrations. We sort of recovered a little bit. I don't think I've put any slides on it today. I think I've left it out, but it's another thing from year 11 you sort of need to know how to do. So really important you know your titrations. Again, this is all the stuff from the study design. And then these are the chromatography slides. I'm not going to spend too much time on them. I want you guys to sort of, if you feel like it and you feel like you need it, please go over these slides. They have all the information you need, but that is all year 11 stuff that you should be able to revise yourself. So let's jump in to this. Spectroscopy. How do we identify? So we use chromatography, we've separated all our mixtures, and now we're going to figure out what are our mixtures. What have we got? So we use spectroscopic techniques. Now, this is just referred to as spectroscopy. Now, they use different forms of EM radiation or electromagnetic radiation, and they find what's going on. So if we have an unknown organic molecule, what might we be useful to identify it? Well, we want to identify the molar mass, we use mass spec. We want to identify the functional group, we use IR spec. And we want to identify how it all connects together. How are the molar mass, where is the functional group in it? Where are just the carbons? How many carbons? Are there other things? That is all the connectedness is NMR. NMR is really, really confusing. Mass spec is, I'm going to be honest, it's really simple to get your head around it. Most of you will probably come out of today understanding it. If you don't, that's okay, but you will understand mass spec pretty quick. IR spec, also sort of simple. It's a little bit more difficult, so it might take you a little bit longer to switch onto it, but it is also something that I expect, 30-40% of you to come out of today and say, hey, I understand IR spec. NMR, if you come out of today understanding NMR with the very little information I'm going to provide you, because we're not going to go over it in super detail, then very, very impressive, because NMR is really confusing. And it takes a little bit. It'll take you 1 or 2 or 3 times of going through it to really get your head around how it works. And we're not going to go through it in super detail today. Now, what's really important about these 3 as well, there are a couple of slides in here on sort of how these things sort of work. What's really important is just have one sentence on how they work. They are really complicated pieces of machinery. There are multiple things that happen, and it is really, really, really confusing. So please just take, a good 30-second, a good couple of minutes one day when you're going through it to write out a singular sentence of how it works. So then in your head, you have that singular sentence, because understanding how they work and their machinery and all that is useful. It doesn't make it a little bit easier, but it's just a bit over the top, and it's far too hard for all of you to remember. So moving forward, let's look at mass spec. So this is what a mass spec looks like. This is what you're going to be provided with. It looks something like this. So mass spectroscopy is a technique that provides information on the structure and molecular mass of the compound. The mass spec looks like this. So this is what mass spec looks like. We're going to go through what all of these things are and sort of how it sort of briefly works. So mass spec occurs in 2 sort of forms. Now, it occurs in an ionization stage and a fragmentation stage. So what does that mean? Ionization is when you get a molecule, and so you vaporize this molecule, so the molecule is in like a gaseous form. the molecule is moving through a machinery, so maybe a pipe or something, and what you do is you blast it with electrons. So you've got like an electron gun and you blast it with electrons. You hit it really hard with electrons. When you hit it really hard with electrons, you're going to make the molecule unstable, because what you've done is you've knocked an electron off and now it's got a positive charge. It's going to become unstable. Most, not all, but most will break. Most of them will break somewhere. There will be a break. Why is there a break? Because when it breaks, half of it can stabilize. So as you can see here, this has a positive charge. This has sort of stabilized. Same thing here. This is stabilized, and we've got a positive charge on the other end there. So essentially, the dot refers to the one that's stabilized. The plus refers to the one that hasn't stabilized, and it's still unstable, but it's more stable because it's smaller. Now, importantly, I've never seen an exam ask you to write all this stuff out. This is just a good way to get your head around what's going on. Fragmentation causes a cation and a free radical. Cations accelerate through the machine, and they hit a detector. Free radicals are eliminated in the chamber, so free radicals are not detected. The positive aspect is detected. So what's really important is they're not all going to break in the same place. You can have breaks everywhere in different places. There's usually only going to be one break, usually, but it's going to break in different spots. So you're going to get lots of different cations forming. When those cations hit, they hit the detector, and the detector can determine how big they are in molar mass. So MZ refers to our molar mass. As you can see here, there's a couple of things that we should look at. The largest peak here is the peak that has the relative intensity of 100%. What that means is it's the most common. It's the one that's hit the most, so it's the most common. The highest molecular weight peak often refers to the parent molecular ion peak. What does that mean? It means we're like this. This has not broken. And for some reason it didn't break, we didn't get any free radicals, and essentially it went all the way through and got detected as a whole molecule still. And so therefore that molecule stayed complete, and we refer to that as it's the molecule's molar mass, it's the total molar mass. So tiny peaks are usually, plus or minus 1, about, around a peak. So if you have lots of little tiny peaks around a peak, what that says to us is that there are some isotopes. So we talked about isotopes in year 11, just talking about them again, but carbon's usually 12, there are some carbon 13s. Chlorine's usually 35, but there are some chlorine 37, sorry. Bromine is usually 79, but there are some 81s. So it's important to sort of understand that. So in this case here, we have propanol. So propanol looks something like this. So these are all hydrogens. So what's the molar mass of this? Like, without looking at the mass spec, let's figure out what the molar mass of this is. So the molar mass of this is 12, 12, 12, so it's 36, plus 16 is 52. 52 plus 1, 2, 3, 4, 5, 6 is 58. Now, looking at this, what is the base peak? Well, the base peak is here, it's at 58. So funny enough, this molecule here, for some reason, just didn't break that often. It actually was able to sustain its main mass. And then where is the highest peak? Well, the highest peak is actually 59, but it's such a small peak that you'd argue this is an isotopic peak. It's so small you'd argue it's an isotopic peak. So this is actually the biggest. So we're going to refer to this one as our, parent molecular ion. So 58 is our parent molecular ion, which matches up with the molar mass we determined by knowing what it was. So when you don't know what this is, you use this and go, all right, well, you wouldn't be given that. You use this and go, all right, mass spec, which one's the biggest? This one here, 58. Cool, I'm happy with 58. And that's what you go with. So that's how that works there. So isotopes to know is carbon 12, carbon 13, chlorine, and bromide, the ones I've already talked about. As you can see, at our molecular peak here, there are two that are really distinctly big. So you would call this one the molecular peak. However, this one would also realistically be a molecular peak because these are about a 1-to-1 ratio. Yes, these ones are far less common, 99 to 1. This one's 3 to 1, but this one's a 1 to 1. So there's as much bromine 79 as there is bromine 81. So that's why they're sort of equally split. All right. As you can see, ethyl chloride, same thing here. So that is mass spec. So mass spec's really useful in terms of that. You can also determine what other little aspects are there. You could sort of like go, all right, this peak here, what is there? So actually, we'll go back to this one, so it might be useful. We've already drawn out the molecule. What is this peak here? Well, this peak here is 29. Well, if I went carbon 12, double bond to an O, double bond to a H, and let's just say this was knocked off here, it was broken here, well, this would be positive. This molecule would be positive, should have, you know. So this is a positive. This here has a mass of 12 plus 16 plus 1. 12 plus 16 is 28 plus 1. This is 29. So this makes sense. This makes sense that this here is one of our bigger peaks because it makes sense that it's just broken here. You can figure out what your bigger peaks are. So you can actually go through and do that. So here are some other examples. That's mass spec. So as I said, I'm not going to spend too much time on mass spec because it's really one of the more simple ones. And I actually think most of you coming out of this now should really understand how mass spec works. Mass spec is pretty sort of straightforward stuff. It's really just useful for the molar mass. Yes, you will be asked about the largest peak. They do ask about largest peak, as this is a good example where the parent molecular ion isn't the largest peak, which is more commonly what happens. It more commonly breaks. But in these other two examples here, it just happens to be that the parent molecular ion peak is the same as the base peak or the largest peak. So that's essentially that. Mass spec, done, tick. You should be all over that. The one thing, actually no, we'll move forward from that. We'll leave that there. So moving on, infrared spectroscopy. In infrared spectroscopy, we use radiation from the IR range, so it's infrared radiation that we're using of the electromagnetic spectrum. So IR spec is most useful for determining what functional group an unknown molecule has. So in IR radiation that we sort of hit the molecule with, it changes the states of the covalent bonds in the molecule, and it sort of makes it sort of shake around and look a little bit different. So don't worry too much what that means, but it just changes the energy state, and we can detect that change in the energy state. So as I said, it's a really complicated piece of machinery. It looks like it here. I don't want you to worry about that. This is a slide that's here for bonus information. If you want to read through this slide, go for it. But this is just bonus info. You do not need to know this stuff. The things I want you to get out of this is that this sentence here is pretty much all I want you to know. Infrared radiation changes the vibrational energy states of covalent bonds, which can be detected by the IR spectroscopy. That is all you need to write. If you are ever asked to write about how it works, it'll only ever be a 1-mark question, and that is all you're ever going to give. IR radiation changes the vibrational energy states of covalent bonds that can be detected by IR spectroscopy. Full stop. That is all you're ever going to write, and it's all you ever need to know. So that's really important. So, IR spectroscopy also comes up in your data booklet, which is why I have this here. I had this here the whole time and haven't had to use it, but we are going to use it now. So, IR spectroscopy comes up. Where does it come up? Here. So it's on page 11, figure 14. This table here is really important. Now, this table here shows where you are going to find on an infrared spectrum at what wave number, so this is what our axis has, where we're going to find peaks. Now, there are some peaks that are really distinct and you're going to be able to pick them out. We'll discuss those in a bit, but this is a really useful thing that you need to know where it is. As you can see, the further up you go, you get these like more sort of stronger bonds. So, one other thing I'd probably like to ask very quickly as well, and I want you all to have a think about this. Those at home, feel free to pause and have a think. Why do these three, not these two, these three, 1, 2, and 3, why do these three specifically, I know we have our CH, but I don't want you to worry about that too much. Why do these three specifically have such a higher wavelength? Now, I'm just going to give you a clue. Higher wavelength means, there's more strength involved. Why do these three? So for those of you watching the recording, please feel free to pause now and think. Those of you who are not watching the recording or at the premiere, apologies, don't really have time to think. The answer to this is 3, 2, 1. These involve hydrogen bonds. Hydrogen bonds, hydrogen bonds. These can form different molecules between them will form hydrogen bonds. So when there's two molecules there and they've formed hydrogen bonds like intermolecularly, they sort of are able to stabilize a little bit better, even though it's not within their own molecule. You've got a little bit more stabilization, so there's less sort of that vibration. So if you think about it, NOF, remember the NOF rule, hydrogen with nitrogen, oxygen, fluorine. These have oxygens and these have nitrogens. Now, yes, these have oxygens and they'll be able to make hydrogen bonds with other, like there'll be hydrogen somewhere else in the molecule. So when there's two of them, correct, they will. But these ones are more directly involved. So that's why these three have sort of this higher wavelength, just a cool fact. So as you can see here, different bonds have different absorption characteristics and different changes in vibration, which we detect differently. So this is what it looks like. Now, what do you need to know about this? So the plot has sort of percentage transmittant versus the wave number. Don't worry about that too much. The wavelength is just a measure of the frequency, and it's just what you're going to use to compare with this. So you compare this with this along here. That is all you're going to use it for. Troughs are called peaks. So these are troughs, so these are peaks, peaks, peaks. These are all peaks. And these are where we detect vibration. So we've detected vibration there. Now, the other thing that's really important to know is the fingerprint region, which falls at around 1500 or below. Yeah. What do I mean by that? The fingerprint region is actually really, really useful, but it's beyond the scope of VCE chemistry. It's used in university level chemistry, and for those of you who do follow chemistry into university, you're going to see this a lot. However, for our level of chemistry, we don't look at it. It actually tells you about the individual characteristics of it. So I'll show you an example on the next slide, but the individual characteristics between molecules that are very similar, but they're slightly different. The fingerprint region is like its fingerprint. It's like, for example, if you have a twin, you and your twin look very similar, but your fingerprints are different. It's that characteristic that really, really determines the difference between the molecules. So molecules that are very similar, they're like twins to each other, but they're slightly different. The fingerprint region is the thing that determines them. So absorption in this region is characteristic of the molecule as a whole. Peaks above 1500 indicate the presence of particular bonds, which are really important. Pay attention to the intensity and sharpness and the shape of the bonds or the bands. We're going to talk about these in a second. So as you can see here, these are two that have extremely similar functional groups and what's going on, but then look at their fingerprint regions. They're very, very different. These are different molecules. They're very, very similar, but they're different because of their fingerprint regions. So you're going to get this piece of information out of it. You're not going to worry about this. We don't worry about the fingerprint region. The fingerprint region is not relevant to us. We leave it alone. As you can see here, very similar. This is propan 1-ol, this is propan 2-ol. They're so similar. There's just that distinct OH in a slightly different spot, and you get a slightly different ion. So this is a very quick summary of the peaks that you sort of need to know, and we're going to go through examples for each of them. Or we're going to go through examples for like one or two of them. I'm actually not going to go through examples for all of them, but we're going to go through examples for a couple of them. So these are the ones you need to know. So OH alcohols, so this is when it's just an alcohol. You get a big, smooth, but intense, which means it goes all the way down to the bottom, peak at 3,300 centimeters. So it's a smooth and it's big. OH for acids, you get a big dirty peak, and we will show the difference between them, so don't worry. But it's just huge. It's a mess. It sort of engulfs multiple things. So the alcohol as well doesn't engulf. So what it means is that the peak is by itself, and then there'll be another peak next to it, and it sort of looks like a stiletto. So you'll see this one referred to as a stiletto, whereas acids are like a big peak, and they sort of absorb other peaks around it, and it's a bit ugly. CH, it's always a very thin, sharp peak at 3000. It's not very useful. So most things will have a really sharp peak at 3000. It's usually very thin. The acid will engulf this. The alcohol will not. That's a very distinct difference. So this engulfs this. This does not. The NH is an intense peak at 3400. So it's a little bit further on. It doesn't really commonly come up. And then if you get a C double bonded to an O, it's usually a thin, very intense peak at 1750. Now, there are loads of different things that have C double bonded to an O, so there are slight differences in them, but we don't really go over it in too much detail. It's just important to note that that's there. So, And as I said, it's not important to memorize numbers. It's roughly what you sort of expect them to be by looking at the shape. So, as you can see here, these are the ones that they all sort of look the same. As you can see this meme here, it's just trying to say that these ones all look very similar, and it's really tough to sort of determine between them. So don't expect to be able to determine between them. You might be able to get a little bit of information out of it, but really, if you can just determine there's a C double bond to an O, so a carbonyl group somewhere, we're good. That's really good if you can determine that, and you can move on from there. So, an example of propan-2-ol, as you can see here, propan-2-ol is an alcohol, and this is this stiletto shape. It's like this is the heel, and then this is the shoe. Like, it's a terrible, terrible drawing, but that is that sort of stiletto shape that we talk about. This is a really smooth peak usually. It's around 3,300, and it doesn't engulf that really thin CH bonding peak. Doesn't engulf that. It just has its own smoothness, and it's by itself. Now, if we go to a carboxylic acid, notice how, first of all, there's no peak here. This one, there's a peak here. That's telling me there's a carbonyl group. So there's a carbonyl group. That peak there is distinctly a carbonyl group. And then I have this really big, dirty bond that's, somewhere around 3,000, 3,100. I'm happy with that. It's a really dirty, big peak. This is going to be a carboxylic acid. And then lastly, we just have a carbonyl group here. As you can see, here's your CH. It's not very big. It's in this one here, it's actually not very intense, but you've got a CH. There's nothing else really here. This isn't big enough to be anything. There's nothing going on up here. But then you have a really strong, thin bond at about, that's just above 1,600. So being just above 1,600, you can say, all right, actually it's just above 1,700, apologies. That's definitely a carbonyl group. So you've got a carbonyl group there. In this case here, it's acetone, which is propan-1, because it's a ketone. And that's how you go about that. So as I said, IR spec, it's the first time you see it, it can be really confusing. And it's especially this. This is what confuses lots of students, but don't worry too much about this. You want to be able to determine this from this. You want to be able to determine that this is not one of these two. So comparing these three is really important. Being able to determine if it's just a CH or if it's one of these two. Being able to determine whether it's an acid or an alcohol. And then being able to determine whether there's just a carbonyl group. They are the three things I want you to be able to do. Now, you may get this, but this will just be very different. There'll be something really far along, and it won't look like either of these. And you'll be like, something's a bit different here. That's when it's a bit different. But the main three things I want you to be able to do is determine if it's one of these two or this, which of these two it is, if it is, and whether you've got a carbonyl group. They are the three things I want you to be able to determine with an infrared spectroscopy. It gives you the functional group. So you've already seen a mass spec, you've got the mass, you got the molar mass, and then you get the IR spec, you get a functional group. You'll be like, oh, I could nearly determine the molecule from here. But you may not be able to determine the exact sequence of it. Like, where are things in relative space to each other? So sort of like that three-dimensional thing we were talking about earlier. But in this case, we're like, all right, where does one fold fall compared to the other? And that's where you need your NMR. But out of this, mass spec, molar mass. Mass spec doesn't actually use EM radiation, so it's a bit weird that it's called a spectroscopy, but we still do. IR spec, vibrational energy states via IR or infrared radiation, and it's all about functional groups, and you need to know those three different ones, the three different things I want you to be able to determine. Then we move into NMR. So NMR stands for nuclear magnetic resonance. Now, NMR uses radio waves, ultrasound radio waves. NMR uses radio waves. Now, NMR stands for, for some reason there is a question and I put the slide in the wrong spot. Whoops. Anyway, actually, before we start NMR, we'll do this question. I don't know why I put the question after it, like 78, 79. I think I was going to be on 78. I did put this question in and then completely forget to move it. I do apologize. Let's do this question. What type of molecule is this? That's all I want you to know. I don't want you to tell me what molecule it is. I want you to tell me what type, what class of molecule, what homologous series does this belong to. This shouldn't take more than 15 seconds. So you've got 15 seconds in the top right. Those of you watching the recording, feel free to pause. You got 15 seconds, top right. All right. This is carboxylic acid, because we've got a big dirty peak here, and we've got a peak at about 1700. So this is about 3000, this is about 1700, this is a C double bond to an O, this is a, this is your OH for your acid, but it's engulfed your CH bonding. So that is what's going on there. Right, now moving back, sorry. NMR. So NMR stands for nucleic magnetic resonance. It's a very powerful technique. It's a very expensive technique to work through, but it's very useful. It yields information about structure and functional groups. So you can also get functional groups from this, but it just mainly tells you where the structure is. And it sort of tells you about the arrangement of things. Now, the basics. It uses radio waves. And so it's not high enough energy to change electronic or vibrational states, but it's exactly the right amount of energy to change spin states of nucleons. So what you're going to say for this is NMR uses radio waves to change the spin states of the nucleons, full stop. That's all you're going to write. That's your one sentence. So for IR spec, it was about IR radiation changes vibrational states, which can be detected. Here we're going to talk about radio waves change the spin states of nucleons, which can be detected. So it's just using what type of radiation is used, what changes to the molecule, and then it can be detected. It's as simple as that. Now, this affects carbon-13 and hydrogen-1. So these are the two things that it affects, and we're going to discuss this in a second. So energy absorbed depends on the surrounding around the surrounding atoms, gives an important information molecules are connected. You know, it's like 2, 3, 1, 1, 2, 3, whatever it is. So what's really important is just quickly to understand that radio waves are really low. They've got a really low amount of energy. So notice how infrared's got a decent amount of energy. Light, like it's less than light, but it's still a decent amount of energy. Radio waves is really, really small. They don't really have a lot of energy. So that's why it only changes spin states rather than, you know, going through everything else. Now, this is a slide on how it works. I'm not too worried about you guys, you know, having, again, understanding this. Feel free to read through it if you'd like. I'm just going to skip over it. So NMR is super confusing to start with. In order to understand it, we need to first learn about a few different concepts. So please do not worry if today you don't understand NMR. It's just trying to give a brief overview. So first of all, we'll start off with proton NMR, because proton NMR, it sort of gives a little bit more information than your carbon NMR, and it's more useful, so we are going to go through it more often than your sort of, wait, what got mixed up? Oh, we'll just go through proton NMR first. So proton NMR refers to hydrogen-1 NMR. It shows peaks as chemical shifts. So what you've got is this shift. So you've got 0, and then everything shifts across. Note that each peak sort of corresponds to a different area in your molecule. So notice how this is referring to this, and this is referring to this. Now, proton NMR is far more useful. It's going to be the one that you cop more often. Now, there are splits here, and there are, you know, different things in different spots. Why is that? So let's just discuss very briefly what's going on. So the number of peaks refers to the number of hydrogen environments. Now, what does that mean? These hydrogens are in a different environment to this hydrogen, these hydrogens here, because this carbon is connected to different things. Now, if I gave you this molecule here, how many hydrogen environments are there? There's 2. Because this hydrogen is connected to this carbon, is connected to a C2H5. This carbon is also connected to a C2H5 in the same order, and it looks the same. Now this one is connected to 2 CH3s. It's a bit different, so therefore this one is a different environment. I should use a different color. This is a different environment, so there's 2 here. So it's really important to sort of be able to determine that. The peaks then split further, and this is determined by what's around it, and we will discuss this in a second. So let's look at sort of environments. So hydrogen atoms in the same environment are said to be equivalent. The number of environments equals the number of peaks on the spectrum. So you've got a molecule here, which is just ethane. How many hydrogen environments are there? Well, there's 1. We're going to go through all of them. So how many hydrogen environments are there here? Well, if we look at this, This is identical to this. So there is one hydrogen environment. Oh, that sun is really bright. I do apologize. Sun's decided to come out. And then if you look at this one here, how many have we got? Well, we've got one group and one group that are identical, and then this one here is different. So we've got 2. And then here we've got one hydrogen out here doing its own thing. This is very different. So therefore I'm going to say that is on its own. I'm going to say these two are the same because they are very similar. They come off, the same thing. This and then this are different. There's one here and it's coming off 2 CH3s. This one has 2 and it's coming off a carboxylic acid. So in this case here, we've got 1, 2, 3, we've got 4 different environments. So the number of peaks on the spectrum will be 4 for this one. Now, how many carbon and hydrogen environments do we see here? So let's go through hydrogen environments first because that's what we've been discussing. So in our first one, we have 1 because these are all the same. They all come off the same thing, so it all looks the same. In our second one, how many are we going to have? We're going to have 2. In our third one, we're going to have, well, this one's a little bit different because you'd say this and this look the same, but what's really important is this one comes off an OH. This one comes off a CH2 with an OH. So this one is distinctly different to this one. So you're actually going to have 4 environments. Our last one here, we're going to have 2. Now, for carbons, it works sort of similar but a little bit different. You look at sort of the surrounding things that come off it again. So if we go through carbons very quickly, carbons are less common. Carbon here, carbon environments, you've got 2 carbon environments because each of these are the same, but then this one is different. This one here you will also have 2. This one here you will have 3 because there are 3 different environments, and then this one here you will have 2. So sometimes they match up. So as you can see, this one matched up, so hydrogen and carbon were the same. This one here, hydrogen and carbon were the same. However, over here, this one was different because hydrogen was 4 and carbon is 3, and then here hydrogen was 1 and carbon was 2. So sometimes they're different, sometimes they're the same. You cannot assume that they're always going to be the same. Now, the other cool thing here is how do you determine between carbon NMR and hydrogen NMR? Hydrogen NMR has splits. It has these splits. Their peaks split up. Carbon NMR does not. Carbon NMR is just single lines. Now, the other thing about this as well, carbon NMR goes up to a really high number. Hydrogen NMR does not. It usually goes up, sometimes it goes to 10 or 20, but it usually stays pretty low. Hydrogen NMR is more useful on the other reason is that you can get these splits. Now, these splits are determined by this really cool thing called hydrogens, like neighboring hydrogens. So what that means is, I'm going to use this example here because this is a really good example. In this environment here, so this is environment 1. Environment 1 neighbors with environment 2. So this is environment 2, it neighbors with it. If there was a carbon in the middle with no hydrogens coming off of it, for example, it would not neighbor because there's something in between it. But in this case here, there's nothing in the middle, so it neighbors with a carbon with 2 hydrogens on it. So it neighbors with that other hydrogen environment. So how many peaks is this going to have? How many splits is this going to have? Well, it's going to have neighboring hydrogen plus 1. So the neighboring hydrogens was 1, 2. So because it has 2 hydrogens in its environment, it's going to be 2 plus 1. It's going to split into 3, and it has 1, 2, 3. 4. Now, other one over here for our environment number 2, it's going to split of NH plus 1, so neighboring hydrogens plus 1. Neighboring hydrogens is 1, 2, 3, so it's going to be 3 plus 1, which is 4, and it's split into 4. So that's how that works there. So hydrogen does that, carbon does not do that, really important. Now, in the other case here that we drew before, is this one here. Now this has one environment. It's got this as one environment and this is the same environment. So how does this split? Trick question. It doesn't split. This has no splitting ability at all because these are the same environment. As much as they are like, they're separate, they are the same environment. There's no difference between them. And because they are the same environment, there's no ability to split. So that's not neighboring. Those hydrogens are technically not neighboring hydrogens because we refer to them as the same. They're in the same house if you think about it. So there's no splitting here. Same with some of the examples here. This hydrogen is not going to split. Now, you might ask, why is that? Well, there is an oxygen in between the carbon here. So this hydrogen is working off this oxygen. It's a bit of a different one. This is not going to split. This one here would split into 3 because there's 2 here. This one here would split into 6 because there are 5. There's 3 and there's 2. This one here would also split into 3. So that's where this splitting comes into it, and you can sort of figure out by looking at the splits how you can determine what's going on with your molecule. So things are always a little bit different. This one here is also really cool because it splits into 7. It splits into 7 because there are 6. They may be the same, but there are 6 hydrogens that are in different environments to him. So there's 6, and then splits into 7. So, I think that's just a summary of it. Just a bit of a summary of NMR. So let's just briefly go through a question. Like I don't expect all of you to do this. You're welcome to pause now if you'd want to. Those who are at the Premier, you don't get an option. I'm just going to go through this. So what you've got is, this is an ATAR nose practice exam from 2019. And we have a bunch of graphs. So it says a chemical that contains carbon, oxygen, hydrogen. So it's got carbon. It's got 3 carbons to 8 hydrogens to 1 oxygen, and that's just the ratio. So I could have 6, 16, and 2, or I could have 12, 24, and 3. So that's just the ratio that's going on there. Not 12, sorry, it'd be 9. I don't know why I said 12, it should be 9. That's just the ratio. So that is just the ratio there, but that's what we've been told. That's the molar mass, the molecular formula ratio. So looking at this, what have we got? So first of all, the infrared spectrum is shown below. In the table, write the bond responsible for the given wavelength. So the one at 3,325, so the one that's there, that big smooth bond, what do we think? It's going to be an OH alcohol. Really important you put the alcohol in brackets because you don't want to write OH and assume it's a carboxylic acid. Now, what is the bond at 2,962? Well, this is going to be CH. Cool. Moving on, B. The mass spec of the compound is shown below. Write the mass to charge ratio of the base peak. Well, the base peak is your biggest peak. So it's going to be at 1, 2, 3, 4, 5. So 45 mZ. Now, what else can I tell from this? It hasn't been asked in the question, but what else can I tell? What is the molar mass? Well, it's either going to be 59 or 60, I assume. 60 is probably more going to be the answer. So I'm going to write 60 as my my parent molecular ion. Now, that wasn't asked in the question, so it's not relevant to the question, but for me, that's useful. So moving on, what have I got so far? I've got that it's an alcohol, and I've got that it has a molar mass of 60. That's what I know so far. So then it says draw the 2 possible structures for this molecule. Well, 60, if I do this is 36, plus 16 is 52, plus 8 is 60. So it's going to be this. It's going to be C3H8O. So, and I know it's an alcohol. So what are the 2 possibilities? Well, if I have 3 carbons, what are the 2 possibilities? Well, it's either an OH here, or it's an OH on the start. And then there's the other molecules. All right, moving on to C. So I've got propan-1-ol and propan-2-ol are my 2 options, by the way. So moving on to it's given me carbon NMR here. It hasn't given me hydrogen, it's given me carbon, so a little bit different. Carbon NMR. What do the following peaks tell me? Now, we didn't go through this in too much detail because I didn't want to go through it and confuse you all, but you can find this here. So this is figure 15 and figure 16. Now, figure 16 is far more useful because hydrogen NMR is far more common. Notice how it tells you all the chemical shifts. It tells you what hydrogens it's referring to in bold, and there's loads. It goes all the way down to 13. So this is what this is telling you. And it's telling you where the chemical shift is. Same here for carbon. So that's the carbon that is put in there. They didn't bold it because there's not extra hydrogens around. As you can see here, these are that. Now, what's also really important is sometimes you'll get a peak at 0, and we haven't discussed this either. The peak at 0 is TMS. It's a standard. It's what it's used to just compare with. But what we've got here is we've got 1, 2, 3, and it wants me to talk about the peak at 64 and 25. Well, what are the peaks at 64 and 25? Well, the peak at 64 is probably going to be this here. Probably makes sense. So this is going to be R, CH2OH, and then my peak at 25 is going to be looking at this. Oh, you can't see what I'm writing, but that's what I wrote. And then looking at this, it's probably going to be, I'd say, probably this is probably your best, or maybe even this. I'd say it's probably this. I'm going to say it's that. So R, CH2, R. And it would make sense because it's probably fitting into this molecule here. So name the compound that's consistent with it. Well, it's going to be prop-1-ol. And then what is the purpose of the TMS peak and ethanol, da-da-da? What is the complete combustion? I'm going to leave these questions to you. Oh, sorry, you couldn't see that because I had that up. I'm going to leave these questions to you. You're welcome to have a look at them if you'd like. What is the purpose of TMS peak? It's used as a standard, and then you can go through and do the second part there. But that is an example of how you use all your information in a question and an analytical question. This is a pretty straightforward one, but it's a good one to sort of start off on. Nonetheless, that is analytical chem. There's also like volumetric analysis. You're welcome to have a look at it. That's titrations. You guys need to go through that yourselves. This is year 11 stuff, so you can go through year 11 notes and have a look at it. We are out of time for today, so I'm not going to bother going over it. So that's a summary of what we went through. We really just went through this. There are slides on this, and you do need to go over this yourself, particularly this here. They are important to revise and important to make sure you understand prior to sort of going into any sort of 3-4 sort of exams or, you know, all of that stuff. So nonetheless, that is everything for today. So just to summarize,